Vitamins, blood, what is this? Chemotherapy, chlorophyll. I mean, really important things. And most of these lines on there, you see this a lot more in organic chemistry. It's all carbons and hydrogens and things, and nitrogen and phosphorus and things like that in there. But what the key ingredient in all of these is a darn metal atom. If you went to the talk yesterday with Dr. Keith's panel, the metal there he's talking about was tin. And how, man, that is all over the place. Really important. Here, like, for example, look at the blood. If it wasn't for that iron atom, you couldn't carry the oxygen in your blood. So a lot of these compounds, it's that metal ion that really ion. So we're going to do some chemistry with complex ions. And if you've noticed the trend for exam 3, the trend is know how to write a Ka reaction, know how to write a Kb reaction, know how to write a Ksp reaction. Now it's going to know how to write a Kf reaction. And then we're just going to do ice. That's pretty much it, right? And so the idea here is, okay, we have these complex ions, like the iron in blood, okay, and iron's in that heme. Okay, well, does that iron fall apart? Yeah, it does. It dissociates a little bit. It's all tied up in the complex ion, but there's a small amount of free iron floating around. Or if you take an iron pill, what's the effect of that iron on making heme? This is Le Chatelier's principle, right? And so just how much of that free metal ion is floating around? That's pretty much what today's homework is all about. How do you figure out how much of the free metal ion is there? In all these cases, you can do it, okay? And it all starts by writing the complex ion formation reaction. You have to know how to write it, just like we had to know how to write all those other equilibrium reactions. Ka, Kb, Ksp. Okay, the convention. The hint to me is formation. So we have to form the complex ion. So it has to be over here. And then you're forming it. Well, what are you forming it from? Well, you're forming it from the metal, right? The metal ion. And whatever else, right? Look at it. In this case, it's the heme. In this case, over here with anti-cancer drugs, it's everything else, right? It's just pretty much everything else. But they're not going to use the word everything else. They want you to use the word what? It starts with an L. Ligand. Okay? And that's how you make your complex ion. The metal ion and the ligand makes the complex ion. Let's practice a few. Let's write the chemical equation and the Kf expression. So write the Kf reaction, right, and the Kf expression. Here's our first complex ion, a nickel cyanide. So I want to write the complex ion then as a reactant or a product. I want to write it as a product, so you copy it verbatim. Nickel cyanide. There has to be 3 of them. -2 charge. Just copy it verbatim. Then you have to, on the other side, write ligand. Now, there's kind of a trick to this. Do you remember the transition metals? Could they take on pretty much whatever charge it varied, right? Or not? They did, right? Do you remember there's only 2 groups of metals where the charge is fixed? What were those 2 groups on the periodic table? It was group 1 and 2. Their charges were fixed. So that means everything else, iron, nickel, they can take on various charges. We never memorized them, right? Because there's various. So when you write the nickel, I wouldn't start with the nickel. I'd start with the ligand, because you don't know what the charge is on the metal. So let's write the ligand first. The ligand is the cyanide. Now, you might have the charge on cyanide memorized. If you do, what is it? But if you don't have it memorized, right? Look, it's right here. There's a 1 there. Right? Same thing as before. Okay. Now, how many cyanides do I have, though? 3 of them. Look, that number right there. That's 3 of them. Okay. How many nickels do I have? Just 1. Okay. Metals are always positive or negative? Positive, right? Okay, let's figure out what the charge is. Positive something on the nickel. What's the charge on the product side? Over here I have a total of a negative 2. Over here I got to have a negative 2. So the charge on nickel has to be what? Has to be positive. But it's easy just to throw something. I hear a lot of 3s. Just put it in there and find out. You have a positive 3. Now you have 3 cyanides. Each one has a negative. That would give you 0. So the positive 3 won't work. I'll try positive 5. Positive 5 and a negative 3 would be positive 2. Went the wrong way. Plus 1. Exactly. Because then you have a plus 1, and negative 3 is a negative 2. That's the game you got to play. We need to write the... Oh, let's write the KF expressions later. Let's write the reaction down here for the cadmium complex ion. Write it. KF reaction. Complex ion formation reaction. All right, so remember the complex ion has to be the product. You have to form it. And then the ligand, the metal on the reactant side. Yep. We should always write AQ on everything, but we're lazy. Right? You're right, Crystal. We should write AQ on everything. Except what? Solids and liquids. All right? Okay. So hopefully you're writing the complex ion over here. Now there's a trick to this one. What was NH3? What was it called? It was called ammonia. Did it have a charge? No. All right. Ammonium did. That was NH4+. So how many NH3s did you write over? Becca, how many ammonias did you write? The formula tells everybody it's got to be 4. Right there. 4. Okay. How many cadmium? Everybody? Just 1 cadmium. Okay. Oh, let's pick on Sochi. What's the charge on the ammonia? What's the charge on the ammonia? Doesn't have a charge. Trick question. Jessica, how about the charge on the cadmium? She's got the plus. It's got to be plus, but plus what? Here are 2. 4. Here another 2. Right? This whole side is a plus 2. This whole side has to be a plus 2. You're right. It's got to be a 2. Okay. Now I'll write the KF expression. And I think Crystal's really on to something. You should write little subscripts on stuff, because then you know what to and what not to put in an equilibrium constant expression. If it has a charge, it's always AQ, but so we should have it in there. Would we leave anything out in this top one? Or would everything be in there? Yeah, everything would be in there. There's no solids or liquids there. Just write everything. But don't forget those stoichiometric coefficients. So products over reactants, you'd have the complex ion here. And you got the nickel. And you got the cyanide. Now, where did I screw up? Cube the cyanide, yeah. Do the same thing for the bottom one. Product over reactant. Would NH3 show up? Yeah. I like Crystal's comment. I should be writing AQ on everything. Just make sure you read. Your products over reactants, you're going to have NH3 raised to the 4th, right? Cadmium plus 2. Complex ion. So hopefully you wrote something like that. Okay. We're getting there. Whoa. Complex ions are formed when a metal ion reacts with a ligand. Okay. Complex ions have an overall positive. Right? Okay. In each complex ion, circle the ligand, put a box around the metal ion. Okay. Circle the ligand, put a box around the metal ion. So in the top reaction, what should we circle, Valerie? Circle the, what do we say? Circle the ligand. So she's going to circle the cyanide. Then everybody put a box around the nickel. The bottom reaction, circle the ammonia and a box around the cadmium. All right? So this I recognize the difference between a ligand and a metal. Okay. Let's see if we can find the metal ion concentrations in. The whole goal of the homework is going to be find the concentration of the metal ion in complex ion solutions. But we're just going to mess with salt solutions first. But how can you tell the difference between a complex ion and a salt? Now, what's a salt? Salt is just take any metal with any anion. Iron phosphate, right? Iron 3 phosphate. Sodium chloride. Iron sulfate. You know, all those salts we've been talking about. Potassium chloride. They're all salts. They don't have a charge, right? Well, I guess I just answered the question. How can you tell the difference between a salt and a complex ion? The complex ions always have a charge, right? That's the easiest way. Practice a few. Circle each complex ion solution below. So, Crystal, what solution or solutions would you circle? A, B, or C? Circle C? B? Does everybody agree? The complex ion has to have a charge. There's only one up there that has a charge. A, right? Right? Circle a complex ion. So this is the only one you're going to circle. Determine the metal ion concentration only in the non-complex ion solutions. Okay. So we want to find the concentration of the metal in B and C. Oh man, is this a KSP problem? It's not. There's two indicators why it's not. Does anyone see why it's not? Yeah, exactly. There's a perfect one. Nitrate can't be a precipitate. So you can't be a KSP problem. The other indicator is, to me, big M. It's a solution. It's not a precipitate, iron 3 nitrate. So there's another hint. Okay. I guess there's another hint. You try to look up a KSP for iron 3 nitrate, and you're never going to find one. So, okay. We want to know the concentration, then, of the metal. The metal's iron, but what's the metal's charge, Kathleen? Look at the formula. It tells you. 3. Yeah, right there. Got to be plus 3. Okay. Now, the iron 3 nitrate. Notice the ratio is 1 to 1 for iron. For iron and iron 3 nitrate, if you one iron 3 nitrate breaks up, you get 1 iron 3. So the concentration of iron 3 must be 0.85. Exact same thing. Oh. They didn't ask for this, but I'm gonna, just because I'm not the nicest person. What's the concentration of the nitrate? Okay, let's put it down there and see what it looks like, 0.85. The problem is that there's 3 nitrates. Albert sees it. There's 3 nitrates for every 1 iron 3 nitrate. So it's going to be 3 times as concentrated. You have to multiply it times 3. Okay. Let's try this one. Cadmium. Jose, we want to know the concentration of cadmium. What's going to be the charge of the cadmium? Yeah, +2. So there it is right there. And everybody, what will be the cadmium 2's concentration? 0.1. What would be the concentration of the nitrate? It would be 0.2. Yeah. Okay. So we've got an idea here of telling the difference between complex ion solutions and salt. One has charge, one doesn't. Okay. This is the meat. This is what all the homework is going to be messing with. Find the metal ion concentration in complex ion solutions. Okay. You need a game plan. We're going to write the 1 over Kf reaction. That's the complex ion dissociating, falling apart. The reason why we do that is because when we do our ice table and we write our x's, you like to write positive x's and negative x's. Negative x's for the reactant, positive x's for the product. So let's stick with that. The book is sticking with it, so we should stick with it too. If we don't write 1 over Kf reaction, we have to flip what we were doing. We have to write, what were we doing? We have to write positive x's for a reaction. Let's just stick to what we were doing in the past. Let's write 1 over Kf reactions, and then we don't have to remember anything. We do the ice exactly the way we've been doing it in the past. So much better. So 1 over Kf reaction. Pretty much, then the complex ion is no longer a product. You have to write the complex ion as the reactant. That's the 1 over Kf reaction. Set up the ice table. And if there's any metal there present, we have to convert it all to complex ion and place that as the resulting initial complex ion concentration, and then figure out the remaining ligand concentration. Put those in the I row. We'll worry about that when we get to the homework. It'll be a lot easier when we see what problems do. And then we solve, figure out what x is. Note that these examples are part of the homework. When I get through them, and then that'll be pretty easy homework. But here's the first one. Kf for the complex ion nickel cyanide is 1 times 10 to the 31. What's the concentration of nickel in a solution initially? 0.9 molar nickel cyanide complex ion. Okay, so I just scribbled down the steps there so we can follow them. The final answer is nickel 2 is 2 times 10 to the negative 7. Hopefully we'll get that. Let's write the 1 over Kf reaction. Okay. So, Daisy, we want to write the 1 over Kf reaction. So what would you write as the reactant? Yeah, that complex ion. Ni and 4 CN. Okay. And then as products, Sochi, what would you write for the products? do the ligand first. Cn minus, and how many of them? 4 of them. Okay, now we have a nickel. I goes down below. Nickel. What charge has to go on that nickel? Ray says +2. Do you agree? Yeah, because what plus a -4 will give us a -2. Yeah, +2. Okay. So we're done with the first step. Set up the ice table. And if the initial metal is present, let's ask you this. Grace, what would it look like in that question? Let's ask you this first. Is there any initial metal present? Grace. What's present initially? Just the complex ion. Do you see that? The only thing up there initially is this stuff. Right? All you do is look for a big M, look for a solution, and it's the complex ion. That's all that's there initially. What I want to do is change the question, Erica. If the question, and it's coming, you know it's coming, I want there to be initial metal there present. So what would it look like? I mean, let's say it's 0.28 molar initial metal. Now our metal's nickel, but they're never going to, this is what I'm asking, Eric, they're never going to make it that easy. 0.28 molar nickel 2. No. They're going to write nickel what, Erica? Nickel, not complex ion. It has to be initial metal there. It has to be a salt. What anion can I put with anything and it'll always dissolve? Nitrate. It's going to look like this. NO3, and I need a little 2 down there. Right? But that's not, it's not there. But that's what I'm saying. That's what's coming. That's how you have initial metal there. So just trying to help you read these questions. But anyway, there's nothing there. So you can go ahead and do it. So how do we fill in this initial row, Albert, if there's no initial metal there? What are you going to do? Dashes everywhere? We have a solution. We have a 0.9 mole or something. Yeah, put the 0.9 under the, whatever this thing is. All right. Now the other guys are dashes. We always did what for the change row? Crystal, what are you going to put under the change row under the complex ion? -X. And for the nickel, you'll put a +X. For the cyanide, +4X. So the same thing we've been doing. The equilibrium, our answers, concentrations at equilibrium, add things up, see what you get. 0.9 and a -X. X and nothing is X. 4X and nothing is 4X. Okay. Now we have to solve. So we're done with this step. Now we just solve. How are we going to solve this? Kathleen, what are we going to do? Yeah, the expression, the KF. Well, not the KF expression, the 1/KF expression. All right, let's just write it out so we don't skip any steps at all. 1/KF expression is products over reactants. And that's going to be, all right. What's my product? It will be the nickel. Oh, it's supposed to be a +2, isn't it? And the complex ion. So the reason why this works is because if you flip a reaction, pretty much equilibrium constant, you just flip it then. She caught it. I was trying to see if someone was paying attention. If I had a little Snickers bar, you'd get it. All right? Does everybody agree so far? 1/KF reaction, So that means that the new equilibrium constant is 1 over kf, products over reactants. Okay, now we got to start doing some math here. Okay, so what is 1 over kf? My kf was 1 times 10 to the 31. That has to equal, what are you going to put on top? Jose, what are you going to put on top here? Yeah, good. The nickel's the x times 4x for the cyanide. Good, to the power 4. Then the bottom, everybody, 0.9 minus x. Okay. So let's keep going here. Take 1 times 10, take 1 divided by 1 times 10 to the 31. You're going to get 1 times 10 to the negative 31. If you don't believe me, just try it on the calculator. You'll see it. You get 1 times 10 to the negative 31. Oh, my goodness. Okay, what's x times 4x to the 4th? Ooh, she figured it out. 4 to the 4th, Crystal got 256. And then I'm going to have x to what power? She says the 5th. You agree, Jessica, the 5th? All right. So I have x to the 4th times x. X to the 5th, right? In the end. And the bottom is 0.9 minus x. Okay. Remember dropping the x game. X can only be dropped if you're adding it or subtracting it from a big number. In the numerator, in the top, you're not adding or subtracting x to a number. You're multiplying it times 256. Right? It's almost like 256 times x to the 5th. What's the number you're adding or subtracting it to? 0. So you end up with a really dinky number. There's nothing you can do there. But in the bottom, take 0.9 minus a really small number, you end up with, take 0.9 minus a really small number, you end up with what? 0.9 minus 0.00000, I mean, look at that, negative 31. I got to keep going. 0.0000008 with 0.9. So this guy, that's the only place you can drop. This is approximately 256 x to the 5th over 0.9. So Daisy, how do we solve for x there? Okay, take 1 times 10 negative 31 times 0.9, then so how do you get rid of the 256? Remember the diagonal story, right? Where do you move the 0.9, Daisy? Up to the top. Where do you move the 256? To the bottom. Yeah. All right. So what the heck is that going to be? 1 times 10 to the 31 negative. Take it times 0.9. Divide it by 256. About 3.52 maybe, times 10 to the negative 34. Okay. Now I need to solve for x. Ooh, to the 1/5. Exactly. All right? Take both sides to the 1/5 power. Now, there's a trick to this. Let me show you. Unless your calculator can do 1/5. Just not to skip any steps, right? On my what's 1/5? 1 divided by 5 is 0.2. So really, you're raising this to the 0.2 power. Now, my calculator can do that. I don't have a fifth root button or a 1/5. So what I'm going to do is set x to the y. Right? You can raise any number to any other number to the y button. I just put in 3.52 times 10 to the 34. Right? Put that in there. Then I want to raise it to the 0.2. So you just push x to the y, put in a 0.2, and equal, and you got it. So my x is about 2.04 times 10 to the negative 7. Now, Juan, is that my answer? They want the free metal ion floating around. Pretty much you have to look at the ice table. Yeah, he's right, because it's just X. All right, because nickel is just X. So that's my answer. Okay, that's my answer. So in working these out, pretty much write the 1F reaction, and set up the ice table and solve it. Now there's a twist to these, and here's the twist. Same thing. We have a 0.1 molar cadmium nitrate. Same thing in the sense we want to find the concentration of the. But this cadmium nitrate solution is mixed with 1 molar ammonia. What's the concentration of cadmium in the mixture? And they tell us the Kf for this complex ion, 1 times 10 to the 7th. Our answer is 7.7 times 10 to the negative 8, but how do you find the free metal concentration in a complex ion solution? Pretty much. So let's just start. The 1/Kf reaction is what you got to do first. So do we write the complex ion? Yeah, the reactant side. Cadmium. 4 ammonias has a +2. In fact, we've done this one already. We ended up with 4 NH3s. Do you remember what we're looking at this? What's the charge on the cadmium have to be? It has to be +2. Okay, so there's our 1/Kf reaction. 1 cadmium, 4 ammonias. Now we have to set up our ice table. I'm leaving some space because look at the directions in that second step. Do we have set up the ice table, and if initial metal is present, convert it all to complex ion? Do we have any initial metal present? Do you see it, Jose? Yeah, here it is right here. Notice this cadmium nitrate is not this thing, right? Here's our complex ion. We don't have it there initially. What we have initially is this solution and this solution. That's what we have there initially. Okay? So just to try to make this a little bit stepwise and logically, let's just put those in there first. That's why I wrote my I row a little bit lower. Let's just put this in first. We have 0.1 there, and we have 1 there. Right? Because we're supposed to convert all the metal to complex ion. The reason why you do that is, look at those Kfs. They're huge. If you have any metal there, it just gets sucked up by the ligand and forms a complex ion. It's like a precipitate. So we can't have any free metal floating around initially. So it all has to get converted to the complex ion. So if we have And we have a lot of the ligands, right? We have one molar comparison to 0.1. So you've got excess ligands. It's always like that. So that way you can convert all the metal to the complex ion. So if we have 0.1 molar cadmium, what's the concentration of cadmium complex ion can we make? The ratio is 1 to 1. It would be 0.1, right? It all gets converted to him. So we're going to have nothing left, all right? In fact, let's not cross them out. Let's show the math, all right? We'll have 0.1, we'll have 0.1, and you're left with nothing, right? Okay. The ammonia, it has to react. So I got to subtract something out. This try 0.1, right? The problem is it would just be, ammonia would be reduced by 0.1 if the ratio is 1 to 1. If there's one ammonia for every one cadmium to make our complex ion, we just subtract 0.1, we'd have a final answer of 0.9, and we'd be done. But dang, it's not 1 to 1. So that means that 0.9 is wrong. It's going to be 0.1 times what? 4. Good, you see it. Times 4. Because you need 4 ammonias for every 1 cadmium. So that means actually 0.4 ammonia is going to react on you. So 1 minus 0.4 is going to be 0.6. There's my initial numbers. Okay. So let's make let's clean this up a little bit. Make a better ice table here. My ICE. So under the complex ion, I'm supposed to write what initially? 0.1. Under the metal, I should write what initially? Dash or 0. And then under the ammonia, I should write 0.6. Okay. So it's an ice problem, but it's little work to set up the initial row when you have metal and ligand present instead of just the complex ion like we did in the previous question. Okay. The change row, we put in what for reactant? Yeah, X is negative or positive? Negative. So X, the ammonia is going to be 4X. So 0.1 minus X. X and nothing is X. 4X and 0.6 is 4X plus 0.6. Or 0.6 plus 4X, same thing. Okay. Now we're ready for our, what did we write? The KF. But not KF, we write 1 over KF. Okay, so I just write it so don't, otherwise I'll end up screwing up. I know myself. I'm not going to skip any steps. 1 over KF is going to be what over what? Product over reactant. I'll have cadmium. And I'll have ammonia, but raised to the 4th. And then I'll have my complex ion. If I don't do this, I just have a bad feeling. Okay. Now my KF was, there it is, 1 times 10 to the 7th. So if we start plugging in some numbers here, I'm going to have 1 divided by 1 times 10 to the 7th. My cadmium concentration is just X. My ammonia concentration is good, 4X plus 0.6. And don't forget to raise it to the 4th power. Divided by 0.1 minus X. Good. Okay. So you with me so far? This is looking really ugly, isn't it? Okay, take 1, divide it by 1 times 10 to the 7th. You get 1 times 10 to the negative 7. Okay, equals x times 4x plus 0.6 to the 4th all over 0.1 minus x. Okay. Can I drop x's? Yeah, good deal. Okay. This is a good one. What can I drop? I can drop the negative x. Does everybody agree with that one? Yeah, there's one. I can drop this guy. So I'll be left with 0.1 on the bottom. In fact, it might look better if you write 0.1 minus 0, because that's what we're kind of pretending it is. That's okay. 0.1. How about the top, though? 4x. Can we drop the x from the front? Just think of plugging it in your calculator. And if it makes a difference, you're screwed. That x out front, you have to plug in that little tiny number, and you multiply it by whatever's in parentheses, you're going to get a different answer on your calculator. Okay? Because you're multiplying something by a really tiny number. That's a big deal. You definitely can't drop that front one. You take 4 times a really tiny number, add it to 0.6, you still get 0.6, wouldn't you? Take 0.0000 times 4, add it to 0.6, you get 0.60000, whatever the number is. You get 0.6. So we can drop this guy. All right? So we end up with x times 0.6. But don't forget to the 4th power. Right? Because x is really, really tiny. You take a really small number times 4, you still have a really small number. It's 4 times as big, but it's still really small. Okay. Let's simplify this guy out. What's 0.6 to the 4th power? Put 0.6 in, and then raise the x, x to the y. Put in a 4. Did you get 0.1296, you said? Okay, 0.1296. Solve for the x. Solve for the x. That whole thing equals 1 times 10 to the negative 7. Take 1 times 10 to the negative 7 times 0.1, divide by 0.1296. I got about 7.72 times 10 to the negative 8. Kathleen, did you get that? Okay. 7.2 times 10 to the negative 8. And according to our ice table, that is the concentration of cadmium. Just X. So we're done. Okay. We went over a little bit. But so there's EX5 as part of your homework then. So have a good weekend.